In multivariable calculus, the gradient vector is a powerful tool used to describe how a function changes at any given point on its surface. The gradient, denoted by the nabla symbol, is a vector composed of the partial derivatives of the function with respect to each independent variable. Visually, the gradient vector always points in the direction of the steepest ascent and is always perpendicular to the level curves of the function. While the gradient shows the steepest path, the directional derivative allows us to calculate the rate of change in any specific direction defined by a unit vector u. To find the directional derivative, we take the dot product of the gradient vector and the unit vector. This result represents the instantaneous slope at that point in that direction. Geometrically, the directional derivative is the magnitude of the gradient multiplied by the cosine of the angle between the gradient and the chosen direction. The rate of change is maximized when the direction aligns with the gradient, minimized when it points exactly opposite, and zero when moving tangent to the level curve. Let's look at an example. For the function x squared plus y squared at point 1, 2, the partial derivatives give us a gradient vector of 2, 4. If we want the slope in the direction of the vector 0.6, 0.8, we dot it with our gradient. The result, for point 4, is the slope of the surface in that specific direction. In summary, the gradient defines the local geometry of the surface, providing the direction of maximum growth and the foundation for finding rates of change in any direction. Understanding gradients is essential for optimization and physics. You are now ready to apply these vectors to complex surfaces. Generated by Vision Solve AI.